Can the universe borrow energy? Can something exist without fully existing at all? At first, those questions sound like word games, like tricks of language, but in modern physics, they point to something deeply real, something unsettling, something most people misunderstand. You've probably heard of the uncertainty principle. It's one of the most famous ideas in science. The usual explanation goes something like this. At very small scales, we can't measure things precisely. The act of observing interferes. Our tools disturb what we're trying to see. And while that story sounds reasonable, it's also incomplete. In some cases, it's simply wrong. Nowhere is that misunderstanding clearer than with the energy-time uncertainty relation. Many people think it means scientists are bad at measuring energy quickly, or that time is just another variable we can't pin down. Others assume it's about experimental limitations, noise, or human ignorance. It isn't, not even close. This principle is not about what we fail to measure. It's about what the universe itself refuses to allow. Even with perfect instruments, even in principle, you cannot have a state with perfectly sharp energy that is also pinned to a perfectly sharp timescale. This is not about clumsy measurement. It's about what sharp can mean for a process that actually evolves. And that last part is where things become truly strange. We tend to think of the vacuum as calm, inert, and featureless. A background of nothingness where events simply don't happen. But the energy-time relation tells a very different story. It says that even the emptiest possible region of space cannot be a perfectly classical blank. A perfectly featureless, perfectly still, dead zero, held forever, is not how quantum reality behaves. What follows from that single idea reshapes how we think about emptiness, about existence, and about reality itself. The uncertainty is not a flaw. It's a rule, and without it, the universe we know could not exist at all. So, what does the uncertainty principle actually say? To answer that, we have to strip away the myths and return to the core idea before energy and time ever enter the conversation. Because long before Heisenberg spoke about energy, physicists were already confronting a deeper problem, the limits of precision itself. The uncertainty principle is usually introduced through two quantities, position and momentum. Position tells you where something is. Momentum tells you how fast it is moving and in which direction. In the everyday world, this seems simple. If you throw a ball, you can measure where it is and how fast it's moving without much trouble. Classical physics assumes that, in principle, both can be known exactly at the same time. At the quantum scale, that assumption collapses. Heisenberg's principle states that the more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. This is not a statement about clumsy experiments or poor technology. It is not something we will fix with better microscopes or more advanced detectors. Even in a perfect universe with perfect instruments, this limit would remain. This is where the most common misunderstanding appears. People assume uncertainty means ignorance, that it reflects a lack of information. But quantum uncertainty is not about what we don't know. It is about what cannot be known in that classical, perfectly sharp way at all. To understand why, it helps to think in terms of focus. Imagine trying to illuminate a dark room with a flashlight. If you narrow the beam into a tight point, you can see one small area very clearly, but everything else fades into darkness. If you widen the beam to light up the whole room, nothing is sharply defined anymore. You gain coverage, but you lose detail. There is no setting where you get perfect focus everywhere at once. Quantum systems behave the same way. When you focus on position, momentum spreads out. When you sharpen momentum, position blurs. This is not because the particle is hiding information from you. It's because the structure of reality itself does not allow both to be sharp at the same time. Another way to see this is through waves. At the quantum level, particles are described by wave-like patterns. A perfectly localized particle would require an infinitely sharp wave spike, but such a spike cannot have a single, well-defined momentum. A wave with a perfectly defined momentum must extend infinitely in space. Precision in one demands uncertainty in the other. This is not a flaw in the theory. It is the theory. The uncertainty principle is not an inconvenience we tolerate. It is a foundational rule. It tells us that nature is not built from perfectly defined objects with exact properties waiting to be revealed. Instead, reality is fundamentally spread out, probabilistic, and limited in how sharply it can be described. And this is the crucial idea to carry forward. Uncertainty is not a measurement error. Uncertainty is not a human limitation. Uncertainty is a property of the universe itself. Once you accept that, the leap to energy and time is no longer strange. It becomes inevitable. Because if even position and motion cannot be pinned down absolutely, there is no reason to expect energy, the very currency of physical change, to behave like a perfectly labeled coin either. The uncertainty principle is not about what we fail to know. It is about what reality refuses to allow. What happens to uncertainty when time itself enters the picture? This is where the deepest confusion begins, because the energy-time uncertainty relation is not just a recycled version of position and momentum. It looks familiar, but it plays by different rules. And if you assume it works the same way, you miss what it is actually saying. With position and momentum, we are talking about two properties of a particle at a single instant. Both are observables. Both can, in principle, be measured directly. Energy and time are different. Time is not something a particle has in the same way it has position. You don't aim an instrument at time and record a reading. Time is the parameter that organizes change. Energy is what sets how states evolve. This distinction matters because the energy-time uncertainty relation is not about measurement disturbance. It is not about our clocks being imprecise or our detectors being slow. It is not saying that we fail to measure energy accurately when we rush. Even with perfect clocks and flawless instruments, the limitation remains. The core idea is this: you cannot assign a razor-sharp energy to a state while also insisting it exists only for a razor-thin time. Finite duration forces finite energy width. That is the deal. If you try to pin down the energy of a system with absolute precision, you are describing something that does not change in time the way a short-lived transient does. On the other hand, if a state exists only briefly, its energy cannot be perfectly defined. It becomes spread out, uncertain, smeared across a range of possible values. This is not a technical inconvenience. It is a rule enforced by the structure of reality. Think of energy as a note in music. A perfectly pure note with a single frequency must be played forever. The moment you limit it to a short burst, it stops being a single frequency and becomes a blend. Sharp timing destroys sharp definition. Duration and precision are in direct conflict. Now, apply this idea to empty space. A region of space with exactly defined energy held with classical perfection as a dead, featureless zero would require the kind of stillness quantum theory does not give you. A perfectly quiet vacuum in the childish sense is not allowed to exist as an eternal blank. This is the key consequence that makes energy-time uncertainty so profound. It is not about particles being hard to measure. It is about your intuition of emptiness being impossible to stabilize as a classical nothing. If you demand that a region of space have perfectly sharp energy while also describing dynamics on arbitrarily short timescales, you run into the same wall. Short time means broad energy. The tighter you squeeze the timescale, the less you're allowed to demand a single exact energy. This is why the phrase matters. Your idea of perfect silence is a fairy tale. Quantum theory doesn't allow the vacuum to be a blank page, not discouraged, not unlikely, not maybe. Your classical picture is simply wrong. The universe refuses absolute calm in the way you imagine it. Even in the absence of matter, even when every particle is removed, the vacuum state is not a dead void. It has structure, correlations, and baseline quantum restlessness. This is where energy-time uncertainty is easy to butcher if you tell the wrong story. Position and momentum limit how sharply a particle can be defined. Energy and time limit how sharply a transient process can be assigned a single energy. The message is not about human ignorance. It is not about experimental flaws. It is about the universe enforcing a rule. Sharpness has a cost, and short duration forces spread. And once you understand this, the idea of a silent, empty vacuum begins to dissolve. Because at the most fundamental level, The universe does not permit absolute stillness as a classical blank. So, what happens if we try to create absolute nothing? Imagine taking a region of space and removing everything from it. Not just the obvious things like air, dust, and light, but every atom, every molecule, every particle of matter. Strip it completely clean. No electrons, no protons, no radiation, no heat. What you are left with, by any classical definition, should be a perfect vacuum, total emptiness, perfect stillness. That is what intuition tells us should remain. Quantum physics tells a very different story. Even after all matter is removed, space does not become a dead backdrop. It does not freeze into classical nothingness. The vacuum refuses to be a blank page. This is the shock that energy-time uncertainty delivers. If you insist on describing what happens on very short timescales, you do not get perfectly sharp energy assignments. You get unavoidable spread. You get fluctuations in what can be said about field values. You get a baseline state that is not nothing. As a result, empty space is not empty in the way you want it to be. Now, this is where popular explanations sprint into danger, because you've heard a phrase that sounds like a cartoon. Virtual particles pop in and out of existence. Here's the rule. Treat that as a metaphor, not as literal tiny marbles appearing from nowhere. Physicists often summarize parts of these processes using the language of virtual particles. That language arises naturally in quantum calculations, and it's useful, but it is not literal footage of tiny objects appearing in the dark. The effects are real. The imagery is a crutch, a useful crutch, if you don't worship it. So, what is the honest version? The vacuum is the lowest energy state allowed by quantum law, and even that state has structure. It has correlations, it has fluctuations in fields, not mystical trembling, not magic, just quantum reality refusing to behave like a silent classical stage. Now, you might ask, wait, if there are fluctuations, where does the energy come from? Doesn't this violate conservation? Good. That question means you're still awake, and the answer is no. Energy conservation is not casually broken and then repaid like a prank. The full accounting holds when you treat the whole system correctly. What quantum theory refuses to give you is a clean classical snapshot at every instant. Intermediate descriptions do not behave like tidy film frames. If you insist on a picture, keep it honest. The vacuum is not empty the way your intuition wants. It is a physical baseline state of fields, and that baseline produces measurable consequences. You can prove this with an experiment. The vacuum pushes back. The Casimir effect. At this point, it might still sound abstract. Elegant mathematics. Nice story. But physics demands more than stories. It demands evidence. And there is evidence. One of the clearest demonstrations that the vacuum is physically active comes from an experiment known as the Casimir effect. The setup is surprisingly simple. Take two flat, uncharged metal plates. Place them extremely close together. Remove all air between them. Create the best vacuum possible. Classical physics predicts nothing should happen. There is no electric charge, no magnetic field. Gravity is far too weak at this scale. The plates should remain still, but they do not. The plates move toward each other. They attract. Something pushes them together. Here is the correct reason, without cartoons. The vacuum fluctuations of the electromagnetic field are affected by boundaries. The plates impose boundary conditions. They change which electromagnetic field modes are allowed in the gap between them. Outside the plates, the mode spectrum is different. Inside, the allowed spectrum is restricted. Same vacuum. Different allowed patterns. That creates an imbalance. Different mode spectrum means different energy density and pressure. And pressure differences push. So the empty vacuum produces a measurable force. This force has been measured with high precision, and it matches quantum predictions when you control for real-world complications. Not magic, not vibes. A physical vacuum state, shaped by boundary conditions, producing a force you can measure. Why do so many people get this wrong? Because our everyday experience trains us to misunderstand reality. Think about silence for a moment. You close the door, turn off the TV, stop talking, and you say, "Now it's quiet." In daily life, silence feels real. It feels absolute. So it's natural to assume the universe can do the same thing, turn everything off and remain perfectly still. That intuition works in your living room. It fails completely in physics. One of the most common mistakes is believing the uncertainty principle is just a measurement problem, like trying to weigh flour with a shaky scale or timing a race with a slow stopwatch. I used to think this way too. It feels logical. If the numbers are blurry, the tools must be bad. But imagine trying to take a photo in a dark room. You turn on a flashlight to see better. The moment you do, you change the scene. Shadows shift, reflections appear. The problem isn't the camera. The act of seeing changes what is seen. In quantum physics, this is not a flaw we can fix. It is built into how reality works. Another everyday mistake is confusing uncertainty with ignorance. We assume the universe knows the exact answer, but we don't, like guessing how much money is in someone else's wallet. The amount exists, we're just missing the information. Quantum physics says that analogy fails. A better one is the weather. You can't say exactly where every air molecule will be tomorrow, not because you lack data, but because the system itself spreads out into possibilities. The uncertainty is not hiding behind a curtain, it's part of the system. At the quantum level, reality behaves like that all the time. Now consider emptiness. You clean out a room, remove the furniture, take out the boxes, turn off the lights. You say, "There's nothing here." That makes sense in daily life, so we project that idea onto the universe. Remove all matter, and you expect perfect nothingness. That assumption is wrong. Quantum physics shows that empty space behaves less like an unused room and more like a restless crowd you can't quiet down. Even when no one is speaking, there's shifting, murmuring, motion you can't eliminate. Energy-time uncertainty explains why your demand for perfect stillness fails. The universe does not hand you a perfectly dead blank, not for free, not forever. Another mistake people make is thinking the vacuum is just a background, like the white space on a page where the real story happens. But in quantum physics, the background is active, it fluctuates, it has structure, it can do work. The Casimir effect proves this in a way that's almost mundane. Two metal plates, no charge, no magnets, no tricks, and yet they move. The vacuum produces a force. Empty space behaves like a physical state, not a blank. I was wrong when I thought uncertainty meant sloppy measurements. Wrong when I thought silence was the universe's default state. Wrong when I imagined that reality was solid underneath and fuzzy only because we can't see clearly. These mistakes are understandable. We live at a scale where rest exists, where objects stop moving, where silence feels real. But the universe does not share our intuitions. At the deepest level, reality is never perfectly quiet, never perfectly still, never perfectly certain. And this is the key truth most people miss. The universe does not permit absolute silence. Not in matter, not in energy, not even in empty space. Once you see that, uncertainty stops being a problem to solve and becomes a rule to understand. And that's the astonishing truth. The universe is never silent, never still, never fully certain. Even in what we thought was empty space, fields fluctuate, the vacuum has structure, and quantum processes leave measurable fingerprints. What we call nothing is not the dead blank we imagined. What we call matter is just a temporary pattern in the same underlying fields. Reality, at its deepest level, is motion, probability, constraint, and structure. If this has reshaped the way you think about the world, then imagine what it means for everything else. How energy flows, how matter forms, how the universe organizes itself. Heisenberg's energy-time uncertainty isn't just a strange principle for scientists. It is a fundamental limit on how sharply reality can be described, a reminder that the universe doesn't follow our intuition, and that the silence and certainty we take for granted are illusions. So, here's the takeaway. Reality is stranger and more beautiful than we usually imagine. The next time you sit in an empty room or stare up at the stars, remember, nothing is ever truly empty in the way you mean it. Everything is structured, everything is governed by rules you don't feel. That is the heartbeat of the universe, the same heartbeat that runs through you and through everything around you. If this video changed the way you see the universe, make sure to hit like and subscribe so you never miss another dive into the hidden rules of reality. Share this with someone who loves mind-blowing science. And leave a comment below. What part of the quantum vacuum blew your mind the most? Thank you for watching, and remember, reality is not what it seems. It is a living, fluctuating, energetic web, and now you've glimpsed its true pulse. Stay curious, and we'll keep exploring the incredible, the invisible, and the impossible together.